Hello, students. This is Dr. DA. It's great to have you here, and I'm going to walk you through these activity we're going to do regarding the drawing of Lewis structures. We learned in class that Lewis is a model in which the connections between atoms in the molecule are indicated by single, double, or triple lines to indicate respectively single, double, or triple covalent bonds. And those electrons that are not participating in bonding are shown as lone pairs in the structure. In this exercise, you're going to be given a series of compounds and you're going to be asked to draw the final or the best possible Lewis structure for them. The assignment is found here in your Canvas page. You should be able to download the worksheet along with a template form that we're going to show you how to use in order to arrive at your structures. All right. So please download these forms before we start, and then we can go through the exercise. Okay, this is the form that you're going to be downloading. It has several formulas of compounds, and the goal is for you to draw the structures at the end. Just as a heads up, because we're not going to be able to do this interactively, I'm going to go ahead and call off or cancel out these last two ones. You're not going to have to do these, okay? But if you want to, you're welcome to do it. Just follow the instructions here in the footnote of the handout, so you can make sure that you do the correct structure for this compound called 2-methylbutane. Uh, we're going to skip these. Now let me show you what else we have in here. What we have here is essentially a template form that you can use. And of course, you may have to make more copies of it if you want, or just use it as a template and work on your own scratch paper. You are not going to be required to submit the scratch paper, only this front page here. And I will provide you with the solutions later on so that before you turn it in, you can check your answers and make sure that you don't need to make any corrections, okay? So let's try out ammonia, which is the first structure that we have here. Have a look at this form here. So I'm going to start out by writing what is the formula of ammonia in H3. I'm going to put that here. In box 1, all you're going to do is essentially calculate the number of valence electrons that are going to be represented in the final structure. So I'm going to separate here the atoms that I have. I have nitrogen and I have hydrogen. There is 1 nitrogen and 3 hydrogens. Now I had to find the number of valence electrons. And you'll remember that what we do is we go to the periodic table and we look at the group number up here above. And for example, we see that for nitrogen, it's group 5A. That means that it would have 5 valence electrons. And for hydrogen, it's group 1A, which means it would have 1 valence electrons. Don't forget to have that periodic table with you throughout the exercise, okay? Just in case you don't remember where these things are. Okay, so we have nitrogen at 5 valence electrons, hydrogen at 1 valence electrons each. So you have multiply that out, you get 5 total electrons coming from nitrogen and 3 valence electrons coming from hydrogen for a total of 8 valence electrons. That is all that you do for this box. All you're trying to do is calculate the number of electrons that will be present in the structure. Now for your next step, we're going to draw the skeleton structure. We're going to put the atoms not in a linear way, but in a symmetric way, and we build from the center outwards. Typically, the central atom is going to be the less electronegative one, with the exception of hydrogen, because hydrogen will never occupy a central position. So that means that nitrogen is going to be our central atom. So I'm going to put nitrogen here, and I'm going to put the hydrogens around it, and I'm going to put them in this way, left, bottom, right. I could have put them left, top, right. I could have put them top, right, bottom. It doesn't matter what order. The point is that we join them with a single line to the central nitrogen. All right. I'm sorry, I had a connection problem and I had to restart. So we are sitting here on the skeleton structure of ammonia with the 3 hydrogen atoms connected by single lines to the nitrogen atom. Each bond represents a pair of electrons being shared. So the number of electrons used for this skeleton would be the number of bonds times 2, which in this case 3 times 2, which is 6. And that is as far as that box goes. We're not going to do anything else there, all right? We're going to go to step 3. It's going to ask us, what was the total number of electrons that have to be present in our structure? From box number 1, we said it was 8. How many electrons were used in the skeleton? In step 2, we said it was 6. So we're going to subtract, and we're going to see that there are 2 remaining electrons to be added. And that is as far as that box goes. Now we go to step number 4. And we're going to say, we're going to add the remaining electrons. First of all, we're going to add them as lone pairs. In other words, 2 at a time. We're going to add them evenly on all atoms except hydrogens, because hydrogen can only take a single covalent bond, and that's it. It is maxed out. So I'm going to redraw the skeleton here. I have 2 electrons to place, but they cannot be on the hydrogens. So that means I'm going to put them on the nitrogen. And now what I'm going to do is I'm going to go to step number 5, and I'm going to check for octets. Does every atom except hydrogen have an octet around? If the octet rule is satisfied, we are done. So we can see here that nitrogen has 2, 4, 6, 8. It has a full octet around it. So therefore, the structure that we drew here in step 4 is the final one. And so what we do is we write it again here. And that is the structure that you're going to copy over to your sheet that you're going to be turning in. So you're going to come back here and we're going to draw ammonia again. This is just the final structure, okay? Please do not put any work on this page, just your final structure. And please do it in pencil so that if you had to make any corrections, you can erase and put them in so it'll stay kind of neat. All of your work should be done on separate pieces of paper, and you don't have to turn those in. You don't have to submit, okay? Let's do another one just to practice what happens when the central atom does not satisfy the octet rule. This is one that is not in your particular worksheet, so I'm going to do a different one. I'm going to do carbon dioxide. Same thing again, and you guys can probably go along with me. Atoms here are carbon and oxygen. There is going to be 1 carbon, there's going to be 2 oxygens. Once more, we're going to use the periodic table to find out the number of valence electrons. We see that carbon belongs to group 4A, which means it has 4 valence electrons. Oxygen, group 6A, which means it has 6 valence electrons. So we have 4 here and 6 here. We multiply out and we find that we have 4 electrons coming from carbon and 12 coming from the oxygen for a total of 16 total electrons in the structure. Step number 2, we're going to build our skeleton. Again, we had to identify a central atom, and that will be typically the less electronegative one. As you can see here on the periodic table, carbon has an electronegativity of 2.5, oxygen 3.5. Also, most of the time, the way the formula is written from left to right kind of gives you a hint that the first atom in that formula is going to be the central atom. So let's go ahead and identify carbon as the central atom, and let's build it symmetrically. Again, we're going to put the oxygens 1 on each side of that carbon. This skeleton will make 2 single bonds at 2 electrons each. That means that we have used 4 electrons out of our supply in that skeleton structure. So we're going to go to step number 3, and we're going to say, well, what is the total number of electrons in the structure? We started with 16. We're going to subtract the ones we used for the skeleton, and that leaves us with 12 electrons to place on our structure. So we go to step number 4. I'm going to redraw the skeleton here. And now I had to place 12 electrons. Remember, there's some rules for this. You had to add them as pairs, 2 at a time. You start from the outside atoms and work your way in. In other words, you don't stop adding electrons on the outside atoms until each one of those has an octet. So I'm going to start with this oxygen here on the left, pair, pair, and pair. And notice that that makes that oxygen have an octet. So I don't need any more electrons in there. Let's go to the oxygen on the right. Notice I'm not going to the carbon, I'm going to the oxygen on the right. Pair, pair, pair. And as you can see, that gives the oxygen on that side an octet again, because you include the ones that it's sharing with the carbon. Now here's the problem. We already added the 12, right? We had 2, 4, 6, 8, 10, 12. And now as we go to step number 5, we notice that the octet rule is not satisfied. The carbon only has 2 and 2, 4 electrons. So it needs additional electrons in order to satisfy the octet rule. It tells us here, change lone pairs into double or triple bonds until the octet rule is satisfied. So what we have here is we have an option here, okay? And I'm going to draw them here, what the 2 options are. In one option, what I'm going to do is, let me draw them in here again. I'm going to take the 2 pairs of this oxygen on the left, and I am going to roll them in, right, both of them. So this is model number 1. And that's going to generate a triple bond between that oxygen and the carbon, with the oxygen keeping a lone pair. The other possibility is that I will take 1 pair from here and 1 pair from this oxygen to generate a structure that will look like this. It'll have oxygen, double bond carbon, double bond oxygen, and the oxygens now are going to keep each 2 lone pairs. How do I decide which of those 2 I should choose? Don't jump to the conclusion yet. Remember that we discussed in class a criterion that is used to determine which of 2 Lewis structures would be more probable. And so that is the criterion of formal charge. To have a little more space, I'm going to do it here on my notepad. Okay, so remember that we have candidate number 1 has a triple bond here, and this oxygen on the right has 3 lone pairs. So we're going to apply the formal charge criterion. And remember, formal charge is the number of valence electrons for that atom minus the number of non-bonding electrons on that atom minus 1/2 of the number of bonding electrons. All right, so let's number these guys. Let's say this is oxygen is A, this is oxygen B, and then carbon is C. So let's start out with A, that'll be the oxygen. Valence number for oxygen is 6. This particular oxygen has 2 non-bonding electrons. And right now it has 1, 2, 3 bonds. So that'd be 2, 4, 6 bonding electrons. So we're going to take half of those. So that would be 6 minus 2 minus 3 gives me a formal charge of +1 on the oxygen on the left. Let's try now the oxygen on the right. So this would be, let's call this guy the oxygen on the left. Let's call this the oxygen on the right. Sorry, that didn't come out very clear here. Sorry. Left. Okay, again, the valence of oxygen is always 6. Now, the oxygen on the right has 2, 4, 6 total non-bonding electrons, and only one pair of electrons being shared, so it'll be 1/2 of 2 electrons. And as you can see, 6 minus 6 minus half of 2 gives us a formal charge of -1. Let's calculate what it is for carbon. So carbon has 4 valence electrons. In this structure, it has no lone pairs, so that'd be 0. But it does have 1, 2, 3, 4 bonds around it. Remember we said that in most structures, carbon always has 4 lines coming out of it, 4 bonds, in any type of combinations. In this case, a triple and a single. So that means that there's a total of 8 electrons that are being shared. So when we calculate that 4 minus 0 minus 1/2 of 8, that's 0. So that means that in this structure, this oxygen has a formal charge of +1, and this oxygen has a formal charge of -1. Okay, so as far as formal charges go, it's acceptable because the formal charges need to add up to 0 for a neutral molecule. The question now is, can we produce a structure that does not have formal charges? So let's look at candidate number 2. Candidate number 2 had us with each oxygen being double bonded to the carbon and each oxygen also having 2 lone pairs. So again, let's go with A, B, and C, and let's see what each of those gives me. Now, notice that both A and B oxygens pretty much are the same, right? They both have double bond and 2 lone pairs. So we're going to say that in this case, our valence is 6 minus 2, 4, or 2, 4, which is 4 non-bonding electrons, minus 1/2 of the bonding one. So each oxygen has a double bond, so that's 2, and 2 is 4. So that means that in this structure, either one of these oxygens, both these oxygens have a formal charge of 6 minus 4 minus 1/2 of 4, which is 0. Let's look at the carbon. Again, valence of 4 minus 0 non-bonding electrons minus 1/2 of, well, it has 2, 4, 6, 8 bonding electrons. So 4 minus 0 minus 1/2 of 8, that gives me a formal charge of 0. So in this structure, the oxygens have no formal charges and the carbon has no formal charges. As we discussed in class, when you have competing Lewis structures, the preferred one, the more probable one, is the one that has no formal charges. So therefore, this structure is a better candidate. The first one resulted in formal charges on both oxygens. So let's go back to our structure here, and we're going to say that our structure that we chose was the one where the oxygens are double bonded with the carbon, and each oxygen has 2 lone pairs. And this is due to the formal charge criterion. So I'm not sure at this point. I don't want to give away too much, but you might encounter a situation where when you are doing some of these, you will find a possibility of competing structures. Just make sure you follow the steps on that template that's going to be on the second page of this handout. And on your work, make sure that you follow those steps, one step at a time. I'm telling you, 95, 98% of the time, that sequence of steps is going to take you to the correct structure. All right. So that is the exercise that we have for this experiment. And hopefully you will get this done quickly so that you can get some good practice even before you go into the homework in the textbook. All right. Thank you very much, and I will see you soon.